Hi guys, welcome to the lesson of partial differential equations. So in our previous classes, we discussed about the canonical forms of parabolic and hyperbolic differential equations of second order. Now we are going to talk about the elliptic equations, right? So for elliptic equations, we know that if the discriminant b squared minus 4ac is less than 0, then we call it as elliptic equation, and the characteristic equation for elliptic equation is given by dy by dx is equals to b plus minus square root b squared minus 4ac over 2a, right? So in this case, we get imaginary roots because of b squared minus 4ac is less than 0. So we use one more transformation to get rid of this imaginary number, that is iota, right? So we'll use one more transformation and rest is same as we did in parabolic and hyperbolic part, right? So let's take an example. So question is given as uxx a plus x squared uyy is equals to 0. So the coefficient of uxx is 1 and the coefficient of uy is x squared. So a is equals to 1, b is 0, and c is x squared. So you'll put into the equation of b squared minus 4ac, and we will check whether it's equal to 0, less than 0, or greater than 0. So 0 is squared minus 4 times x squared is equals to negative 4x squared, which is less than 0 because x squared will always be positive whatever value you provide to x, right? So this negative sign will make this whole negative and it will be less than 0. So we will apply the characteristic equation dy by dx is equals to b plus minus square root of b square minus 4ac over 2a. So b is 0 in this case, so we applied 0 here, plus minus square root of 0 minus 4 times 1 into x squared, right? So this becomes negative 4 square in the square root, right? And divided by 2 times 1 because a is 1, right? So now we're left with dy by dx is equals to plus minus square root of 4 is 2 and square root of x squared is x, and for this negative sign we will write iota divided by 2. So dy by dx, this will cancel out. Dy by dx is equals to either x iota or dy by dx is equals to negative x iota, right? So now we have two roots here. One is x iota and second is negative x iota. So these are separable ordinary differential equations, so we can solve it easily by using separable equations method. So it's y, when we integrate this, we'll get y is equals to x squared over 2 iota plus c1, and for the second equation we'll get y is equals to negative x squared over 2 iota plus c2. Then by similar way we'll isolate the c1 and c2 to construct a function in terms of x and y. Now something that is different from previous lessons, it starts from here, right? So now in the previous lesson, what we did from here, we uh, plug psi in place of c1 and eta in place of c2, and we assume two functions, and then we solve for the equation. But in this case, because of this iota, we want to get rid of this iota. So for that, we are assuming one more transformation, and we are saying that alpha is equals to y plus x squared over 2i, and beta is equals to y minus x squared over 2i, right? And then we will take the average for psi, and we will take alpha minus beta over 2i for eta, right? So by doing this, we can see that this iota will vanish from the equation and we will left with only the real parts, right? So y plus x squared over 2 iota plus y minus x squared over 2 iota divided by 2. So this is alpha and this is beta, right? So when we add both equations, this x squared over 2 iota and negative x squared 2 iota will cancel out. We're left with 2y over 2, which will become y. And here this is alpha and this is beta. So when we will subtract these equations, y and y will cancel out. We're left with x squared over 2i plus, minus x squared. Here it's minus. Uh, let me correct it. It's minus. So negative and negative will become positive, and it will be 2x squared iota over 2, right? So this 2 and 2 will cancel out, I and I will cancel out, so you're left with x squared over 2. So eta is x squared over 2. Now we got psi and eta. Now we can proceed in the similar manner by finding ux, uxx, uy, uyy, uxy, right? So in this equation, we are only given with uxx and uyy. So we only need to find uxx and uyy, right? So for uxx, you know that the equation is u psi psi times psi x squared plus u psi eta times psi x eta x plus u eta eta times eta x squared plus u psi times psi xx plus u eta times eta xx, right? So we will plug in the values. So psi x is 0, so we'll plug 0 here. Then here also psi x is 0, so 0 here, and eta x is x. This is eta x, so we'll apply x here, and then again psi xx will be 0 because psi x is 0, so it will be 0, and then eta xx is equals to 1, right? So we will only left with x squared times u eta eta, right? And here we will left with only this is 0, this is 0, this is 0, this is 0, and here, sorry, u eta will also come here, right? This u eta. So only two non-zero terms, this and this, and here we have only one non-zero term, that is a u psi psi, right? Now we will plug these into the original equation. That's equation number 1. So we found uxx, uyy, so we plug in the values. So x squared times u eta eta plus x squared times u eta eta plus u eta plus x squared times u psi psi, right? So we can take x squared common from this term and this term. So x squared times u eta eta plus u psi psi. Then we can divide whole equation by x squared. So we will get this form, right? So this is the canonical form for the given partial differential equation. And we can see that this is also a second order partial differential equation, right? Having two independent variables. So now we will move on to question number 2. So question number 2 says that 1 plus x squared times uxx plus 1 plus y squared times uyy plus xux plus yuy is equals to 0, right? So the coefficient of uxx is 1 plus x squared, the coefficient of uyy is 1 plus y squared, and coefficient of uxy is 0 because uxy is absent, right? So a is equals to 1 plus x squared, b is 0, and c is 1 plus y squared. Now we'll check for the class of the differential equation. So we'll apply b squared minus 4ac. So b is 0s and minus 4a times c, right? So again, we will get negative 4 times 1 plus x squared and 1 plus y squared. So we can see that this x squared will be always positive. So this value will always be positive because of this x squared is positive and 1 is positive. And again, this y square will always be positive, whatever value you give to y, either is negative or positive because of this square. And with plus 1, this will be positive always. So these both will be positive. Therefore, -4, because of this -4, this equation will always be less than 0, right? So we can say that this is an elliptic equation for the given variable coefficients. Now we will apply the characteristic equation, that is dy over dx is equals to b plus minus b squared minus 4ac over 2a. Then we will plug in the values of a, b, and c, and finally we will get to this form, that is iota times square root of 1 plus y squared divided by square root of 1 plus x squared. So we can write with ones with positive and ones with negative, right? So these are two roots, and this is a separable differential equation. We can see we can separate the variables 1 plus y squared with y and 1 plus x squared with x. So we did, and we got this form, right? Now we can integrate, and we know that the integral of du divided by 1 plus u squared is actually equals to natural log of u plus square root of 1 plus u squared, right? So we can apply the integral here. We will get ln y plus square root of 1 plus y squared, and here you get plus I times ln x plus square root of 1 plus x squared plus c1, right? So we can isolate c1, which is our main phenomena. So c1 will be isolated by keeping it to the left hand side, and then you'll get ln y plus square root of 1 plus y squared minus iota times ln x plus square root of 1 plus x squared on the right hand side, right? So we'll keep this as it is. Similarly, we will differentiate the second root, and we'll get the same thing, but this time there will be a positive sign between them because here is negative, right? So c2 will be equals to ln y plus square root 1 plus y square, which is the integral of this function, plus ln x plus square root of 1 plus x square, which is the integral of this function, right? And we will also place iota here because of this iota, right? So now we have to use another transformation to get rid of this iota. So what we'll do, we will choose beta and alpha. So we choose beta is equals to ln y plus square root of 1 plus y square minus iota ln x plus square root of 1 plus x square, and alpha is equals to ln y plus square root of 1 plus y squared plus iota ln x plus square root of 1 plus x square, right? Now we will apply the same approach, that is for psi we will take the average of alpha and beta, and for eta we will take the difference of alpha and beta divided by 2 iota, right? So by taking the average, we can see that if we will add alpha and beta, so this is positive and this is positive, right? This is positive and this is positive, so these two will cancel out, these two will cancel each other, this and this, because of negative and positive sign, and we will left with 2 ln times y plus 1 plus y squared into in the square root divided by 2. So 2 and 2 will cancel out. We'll left with the finally we're left with the size equals to ln times y plus square root of 1 plus y squared, right? So now we'll work out for eta in the similar manner. We will take the difference of both. So when we'll take the difference, so here you can see that here is negative sign, so it will be positive, and this is positive, so these will be added, and here it will become negative sign. In case here it will be negative, and these will cancel out for alpha minus beta, right? So now we can proceed in the similar manner. We will get eta, that is ln times x plus square root of 1 plus x square, right? Now, after finding eta and psi, we need to identify these derivatives, right? So psi x will be 0 because psi is a function of y only, and psi xx will also be 0, so psi xy will also be 0. And for psi y, I will differentiate this psi with respect to y, right? So we need for psi y, here I'm writing, we need to differentiate dawa psi with respect to y, right? And when we will differentiate this function, what we will get, for we know that the derivative of ln x, that is d over dx times ln x, is equals to 1 over x, right? And or we can write its general form for better understanding. I will write here. So we can write this in this manner, that derivative of ln x power n is equals to 1 over x power n into the derivative of x power n, right? So this is the general form. So we can differentiate this and we'll get 1 over y plus square root of 1 plus y square, that was inside ln, and then to the derivative of this function again. So the derivative of this function will be this, right? You can differentiate and check by your own way. So finally, by simplifying the function, we will left with psi y is equals to 1 over square root 1 plus y square, right? Then we will again differentiate for psi double y, and we'll differentiate this function. So we will get this function at the end result, right? Now we can see that this is our psi double y. Similarly, we'll find eta x and eta double x, right? Then we'll plug in these values into uxx and uyy, ux and uy, right? So this is original equation. Now we'll plug the values. So ux will be equals to this function, that is 1 over square root 1 plus x squared times u eta. Ui will be equals to this function by simplification, and then uxx is this function. This is 0, this is 0, this is 0, so only two non-zero terms, that is this term and this term, right? And again in uyy we will left with only two non-zero terms, that is this term and this term, right? Now we will plug in uxx, ux, uyy, and uy, right, into the original equation, that is equation 1. So this is the form when we will put in the values of respective uxx, uyy, and ux, uy. So we'll get this form, right? And now we can simplify this. So we'll see that some of the terms will be cancelled out. This term will be cancelled out with this term. Same terms with opposite signs, and this will cancel out with this term. Same terms with opposite signs. So we're left with only this term, u eta eta plus u psi psi, right? Only these two terms. So this is the final canonical form, and you can see that from a complex equation we came to the conclusion of a simpler equation. It's a simplified form, and again it's a second order differential equation or second order partial differential equation having two independent variables, that is psi and eta. Right, so it's a form of Laplace equation. If you remember, the Laplace equation was like this: uxx plus uyy is equals to 0, right? So it's same kind of equation, that's Laplace equation, which is also called two-dimensional heat equation. Two-dimensional heat equation, in fact, is in the steady condition, right? The steady condition. So now you can see that how we did this did these problems for hyperbolic, parabolic, and elliptic PDEs. We found canonical forms, we simplified the equations. So hope you guys will learn from this section, and it's very important topic in partial differential equations, because when we will apply the characteristic method, every time we will be using these canonical forms, right? So thanks for watching the lesson and wish you good luck. So it's all for the time being. Thank you.